All right, it's 2 hours UTC and it's time once again for Astronomy Daily Live. So hey, welcome everybody, welcome. Glad you could come in once again to this ever-growing community and a group of really interesting, great people. I do tend to sort of attract some pretty interesting folks, and this forum, this very casual back porch where we have our consumables of choice, always within arm's reach, right? So I've got the hydrogen hydroxide again, the HOH, that well balanced molecule. So it's both an acid and a base at the same time. I don't know how that works, but cheers. Yeah, so hope everybody's doing well. I've got some high clouds that are beginning to roll in from the west, and it's a pretty thick patch. Probably actually not going to be here for another maybe couple of hours, but that's not enough, right? That is not enough time, and there's always clouds are not like solid objects, right? Where there's a beginning and an end. So there's always some fluffy stuff that's really hard to see, even on the satellite loop things, right? Kind of hard to see, but definitely there. And when I'm trying to make very accurate measurements of brightnesses of things, clouds are going to attenuate that light and give me a incorrect reading, and I don't want that. It doesn't do me any good at all, right? Astrophotographers, they can sort of get away with a little bit of cloud, right? Because it's not going to affect their overall quality much. I mean, there are limits there, but oftentimes you can get away with a little bit of cloud, especially if you're in a dark site, because clouds are dark. They're just going to block the light, right? They're not going to necessarily add to the light. They're going to block it. So that's like a couple of lost images, right? But for me, it still is potentially a lost image or two or three, but yeah, that sort of wreaks havoc on any kind of measurement I want. So yeah, I'm just blathering along here, letting everybody get in. So Carolina Sky Astronomy, hey, nice to see you there. Deep Sky Dude, yes. Is it like this? Yeah, I guess it's like that. I don't know all these things. The only ones that I ever use, I use this to an excess, right? This is my go-to peace sign, right? But then, of course, always do this, and of course, you got to be able to do it both hands, right? So there's that. I don't do that one all that much. It just don't have anything against it. I just don't do it. Ingrid, hey, nice to see you from Brazil. Nice to see you near Sao Paulo, I guess, is where she's coming in from. So yeah, hope everybody's doing well. Just Jim, no, I have definitely not. So yeah, not going to do it. Just not going to do it at all, even if there's a chance. So, all right, well, cool. Well, I want to say howdy to Bobby on the panel. Hey, what's going on?
All right. I'm doing good here.
Excellent.
Everything's fine and dandy. Now, we talked about SCRs about a few days ago.
Yes,
I was
sir.
able to do some ACORS data from the airplanes and some ship data of the AIS.
So what kind of data are they relaying?
Well, sometimes in ACORS they relay like their coordinates. Sometimes they relay their messages from the ground station to the air station and stuff like that. And AIS it gives you like where the ships are at.
Like a latitude and longitude?
Yeah.
Very cool. Yeah. So I mean, how far out can you hear those? Can you hear
I
them,
think I
below
can
the
hear
horizon?
them. I can hear them very, very far for sure.
So probably below the horizon, right? So out of line of sight.
Like I said, when I did ACORS today, it was very, very far.
Very cool. Very cool. Yeah,
And the
that's amazing.
AIS, I can pretty much go like usually the lower Chacalaya by Patterson or Calumet, and then like about a few miles north of Morgan City and Berwick will be the Chacalaya, or about a few miles south.
Very cool. Very cool. Yeah, it's absolutely amazing. We're dealing, regardless of what the wavelength or the frequency is, we're dealing with light. So
Yeah.
I definitely
And what's
have.
kind of like a bit cool about like marine, if like marine radio and AIS, is I actually live by where the lower Chapalaya is at, but if you like go like to Berwick and Morgan City, there's the main Chapalaya.
Cool. Cool.
And I
Nice.
can get the Berwick Marine Traffic Control. I think I can get the Coast Guard and some of the marine traffic.
Nice. Is that are those pretty active channels?
Uh, Depends on how many ships there are at sea at the
Yeah, of
river
course.
at times.
Of course. So there can be a lot at one time, and then absolutely nothing for like very long periods of time. Or
Yeah.
I see.
Yeah. Earlier today, I think I caught like 10 ships
Cool.
at the around the river area.
Very cool. Very, very cool. Well, yeah. Well, it sounds like you had a very successful day. I had a very successful day too. Yesterday during the live stream, I was sort of lamenting to the fact that my stacking software wasn't behaving correctly when it came to this galaxy data that I have. The other night, I collected 200 images of M65. And I could actually look. I think they were 3-second exposures. So not a lot of data, but enough to give me an indication of what I'm sort of working with, right? And so I collect the data, but I have to solve two problems. One is the tracking errors, right? So when I lock onto a target, it doesn't stay put, right? It moves around. It tends to drift, right? It tends to drift either up or down, right? Not really a lot of sideways, right? So there's a lot of drift up and down. So if I want to be able to stack these things, right, I've got to take out that drift, right? The other thing that I have to account for is what's called field rotation, right? Because this, you really can't see it, but because, well, yeah, on that one, right? This is an altitude azimuth mount, right? Which means the telescope does this, and then the whole base rotates, right? So it does this and it does this. Well, the sky isn't set up that way. Depending on your latitude, the sky sort of behaves in a different way. So because there's a mismatch in the coordinate systems, what you get is field rotation. So not only are each of these images translating because of the poor tracking, but they're also rotating slightly. Each frame rotates slightly, fractions of a degree, right? Very,
Now, I
very
have
slightly.
a question for you, Cosmic, about when is your SDR coming in?
I don't know. It should be coming in next week, I would think.
You never got the tracking information?
Yeah, we probably did, but it'll get here when it gets here. We'll keep track.
Yeah.
We'll keep track. It's coming from the UK, so.
Yeah. Yeah, that's where most of the SDR plays are from the UK and stuff. Most of your SDRs are mostly European style and stuff.
Yeah.
They were not by RTL. They were not designed to be used as an SDR.
Right.
They're supposed to be designed to be used as a DVB-T receiver used in Europe.
Oh, I see. Okay. Interesting.
And I think the SDR plays are like the same, but they modified it so they can have like the no holds barred style.
Nice. Yeah, I'm very much looking forward to getting ours and getting it hooked up and looking at that waterfall. That's going to be really fun. And
now, how much you pay for your SDR Play RSP2 Pro?
I think he paid. He's getting the metal case, so I think he paid $225 out the door. $225 out the door.
Because I don't have a 1A, but if you follow Danny Shortwave and Radio DX, he's got the RSP1 as well, right. And he was able to get the the 1A metal case, and he still was able to make it work on the RSP1 with the metal case.
Cool. Very cool. Yeah, we're pretty excited to see what this thing can do, and use it as a tool in some of the research and development that we're doing there. So yeah, I think it's going to be a really great thing. Anyways, getting back to the galaxy, right? I ran the images through my code, right? That stacks these images. It does a bunch of other things too, but that's one of the things that it does, is shift and rotate all these images to a reference, right? And I just use the first image as the reference. So everything is keyed off of that, and I register the images, I shift them, I rotate them, and then I add them. And I do that for every single image. So yesterday I looked at the first 10 images or 20 images or something, just to see how it looks. And the stack was just terrible. right? Was that just absolutely terrible? Promising, right? But just not very good. It was having trouble with the rotation part. It was doing the translation part okay, but it was having trouble with the rotation. And so yeah, I got on that this afternoon, and it's like, okay, I'm going to figure that out, and I did. And in addition, I am adding what I think is going to be a really great visual aid for you all, and I can't believe that I didn't think of doing this before, but I will remind everyone, right, who uh, um, has heard this at least a couple of times, and those of you who haven't heard this before, here it goes. Right, the density of matter inside of this head is like neutron star, right? Extremely dense. Takes long time for things to sink in. So this is definitely one of those cases. And what I'm referring to is an image display tool that I have used for literally 30 years, right? It has been around at least that long. It's evolved, right, and it's improved. But what it's called SAO image, and there are different versions of this as it evolved. But this is SAO image version DS9, and yes, that is as in Deep Space Nine. The developers of this image display tool, which I'll show you in just a moment.
And I just want to let you know that shit meow it is online right now.
Good, excellent. Yeah, I'm hoping to join the group over there after this live stream. She usually goes for at least a few hours, so I think.
Yeah, she did a special on Thursday, but I didn't make the time to be there because I want to try to catch that radio special from HARP, the high frequency. I forgot what HARP stands for.
Yeah, I forget too.
Like from Africa, Alaska, yeah.
Yep, they're up in Alaska. Cool, yeah. Cool. Yeah. So did you get any signal? Did you hear anything? Did anybody hear anything?
On the Tuesday one, I was able to catch the 6,000 one, but that's about it.
Cool. So how was the signal? Was it nice and strong, or?
It was okay. Mm-hmm. It wasn't perfect, but it was okay.
Nice. Anyway, so
but it would have been better if those online receivers.
Mm-hmm.
I would have been better off if I caught it with a West Coast receiver.
I gotcha. So okay, well let me set this up. Since I was talking about the galaxy, I will switch to that. But this image display tool is sort of the go-to display tool for anything. It doesn't have to be images. It can be spectra. It can be whatever. There's an interface that you can actually program to if you want. It's absolutely great. Hey there, Justin T. Nice to see you. It's been a little while, so glad you could join us here.
Justin T. It's been a long time from Morgan City.
Yes, sir. So I'm going to share my screen, and I'll show you a SAO image in its in all of its glory here. hide that. I'm going to go over here. So there it is. Let me, yeah, I can do that. So there's, let me do one quick thing here. Let me.
And what is this program called again?
So this is called SAO Image DS9. So yeah, like I was saying, the developers of this code really like Star Trek, so they decided to do that. Anyway, this is a stack of about 170, 180 individual images, and as you can see, you know, I mean, I'm trying to show you, you know, as things are, and let's see if that makes any difference. Yeah, see, I can sort of put that right in the middle there. Okay.
You can still see the wormhole, though.
Wormhole? What wormhole?
That,
oh,
that
yes. Yes, I see the wormhole. Yes. That's okay. Do not fear the wormhole. Anyway, so this is a stack of about 170, 180 images or so. But one of the cool things about SAO image that you can do is you can dynamically change the brightness and the contrast. So if I hold down my right button and move left and right, I change, I don't remember if this is the brightness or the contrast. I forget which. I think that might be the contrast. And if I move up and down, yeah, that changes the contrast. Right, so low contrast, high contrast, and then I can change the brightness. And I can move around, right? So I can...
Now, if... I'm not sure... On this app, can you, like, colorize it without needing GIMP?
Yes, and I'm going to show you those two. You can load up your own color map, but they have some internal ones that are usually adequate. So yeah, so you can zoom in here, right, really close in, and see the galaxy itself. So this is M65, and yeah, we're actually seeing, you know, a dark lane here with a foreground star, right? You can sort of see that here, and it's very elongated, just like it's supposed to be. So yeah, I think this looks pretty good. There are some things that I don't quite understand about it, but I'll, you know, try to. But at the moment, I'm pretty happy with, you know, the signal to noise I'm getting here. One of the things that you might notice, and I can play with this a little bit to exaggerate it a little bit, but you can see how this corner is brighter than this corner. There's like a slope here, right? The background is going from like bright to dark. So I'm trying to understand why that's happening. I'm not quite sure why. But yeah, let's colorize these now. So we can go over here. This, of course, is a grayscale. Here's sort of a rainbow kind of a thing. And I'll zoom in one more like that. So there's sort of a rainbowy kind of a thing. You know, changing colors like this, really what it allows scientists to do is identify things that may not may not be so obvious in the grayscale, right? Now, what that
Now,
might
Jim wants to know, did you use any dorks?
yes, this is completely calibrated. Yeah, and that's actually what I'm looking at in terms of, there's some weird artifacts in here that I'm not quite sure I understand yet. These are probably cosmic rays, just really, really bright ones that came through. So yes, this is dark subtracted and flat fielded. Yeah.
Now,
All
how
these
does
images are.
one get that program that you're showing right now?
You just have to go and do a search for. I think if you do a search for SAO image DS9, I think that'll be like the first thing that comes up.
Now, did you have to use your package management, or did you have to build from a source code?
They actually provide all of the above and an executable. So I just downloaded the executable, and that's what this is.
Okay. Because with my GQRX, I can do the package. I can build it from the source code, or I
Right.
can do a pre-compiled binary.
Cool. Well, that's what you want for sure. So anyway, sometimes the grayscale doesn't accentuate things in the right way. So it's nice to have this option to come in here and colorize things a little bit instead, and it just helps. It helps in the visualization. I don't know if that one does, right? But there's a few preloaded ones here, as you can see. So that is sort of a bluish color map, blue to white. There's one called Heat, which, I guess, yeah, I mean, it's sort of showing it as if it's a little warm. But yeah, there is definitely a dust lane there going right through there. And it looks like maybe there's a little bit of structure here too. I'm not quite sure. So yeah, there's a few others here that can be used.
Now, it's said that you probably won't be able to do true color.
Yes, the only way that I would be able to do true color is if is if I took two other data sets with two different filters, right? So this was actually acquired with the green filter. So I would have to take a similar data set with the red filter and the blue filter.
And then you can try the DS9 thing, right?
Well, then I would actually use GIMP to combine those three and get a color image. But I'm not interested in color images. I'm interested in data. So what I definitely want to do is look at this same object with a different filter, but that would be to get color information, right? So I would take this green image here, right, and maybe I'd subtract it from a blue image, right, and get a B minus V color map. And colors can tell us all kinds of things about the properties of what we're looking at. So that's really the only reason why I would consider, taking more data with a different filter, is to just get the data out of it. It's all about the data, but this looks pretty good. Signal to noise here isn't great, but it's up around maybe 5 or 10 in these fainter areas, and much higher. Signal to noise at the core here is, well, it's approaching like 500 to 1, so that's not bad.
Now, that is a nice, interesting piece of software to use when you're doing some data and stuff like that.
Yes, it is absolutely fantastic. Here is one of the features, is that you can do these horizontal and vertical graphs, and if you look, I'm going to center up on that star. If you look at the bottom and the right hand side of your screen, you'll see a plot, right? So what the bottom plot is, let's zoom out here and make sure we're centered. So the bottom plot is a horizontal cut through this entire image. And that's why if I line my cursor up with the screen, or with the star, you'll see that the bottom thing has a little peak there, right? That's the star. And if you look on the right side, you'll see a similar peak. That is the vertical cut, right? So
now, what if you're able to grab the nucleus?
Yes, I can. There it is, right there. Pretty close. Here, let's we can sort of play with that so I can get right. And I don't know if you noticed this little zoom in box up here in the upper right. That's very handy. Very handy. So there's the center, and as you can see, there are some peaks there on the bottom and on the right. So yeah, that's just called a horizontal cut and a vertical cut.
Interesting.
Yeah. It's a very handy tool. I actually have really only used it for display, but there are ways to get into analysis and.
Yeah, you said you could do custom cover, right?
Yeah, I don't remember exactly how that's done. I'd have to dive into the documentation a little bit, to find out.
Okay. All right.
But it is possible. Let's see, is it like that?
So you could just do your traditional RGB like you've been doing, right?
Yeah. See, here's. Let's see. Yeah, actually, there's a lot of. I don't know what all this is. Actually, color map parameters. Yeah, I don't know.
Try user.
Okay. User. Yeah, there's nothing there. Anyway, so yeah, great tool for image display. A little bit of analysis, quick look kind of stuff. It's really powerful to be able to move the cursor around and change the brightness and the contrast, which is all I'm doing. It's really helpful. Anyway, so that looks really good. I'm pretty pleased with that. As you can see, the stacking software is doing what it should be doing, and I actually used these two stars, that one and that one, as my reference stars. And it did great. It did absolutely great. So yeah, the problem I was having yesterday is totally gone. Totally gone. It was an easy fix.
So I guess this is going to be your thing to do from now on instead of using your own software.
Oh, no. I'm still using my own software to do the stacking. This is just for display. That's all this is. That's all I'm going to use it for, at least.
So this right here is actually going to be temporary, right?
This display? No. This is a new thing. We're going to use this thing a lot, quite a bit.
Okay.
Yeah, because it's really great, to be able to show off things. And I think that this can also show, like JPEGs and all that. But it can also work with FITS data directly. So that's very, very nice. Anyway, so the other thing that I did the other night is I looked at the eclipsing binary star XY Canis Minoris, and I took 1,000 images. So I'm really, really interested in seeing if the variable star actually did its thing, right? The eclipse took place. I'm sure it did, but with that much data, I just wanted to stack them all and see, how faint of a star I could actually get. So that's what I did in this next image. So you can see the result of the stacking here, right? The tracking is off. There's rotation. It's a.
So this one's pretty much messed up, huh?
No, this is actually very, very awesome. I'm going to walk you through a little bit of this.
And we're going to have to say goodbye to Ingrid. Good night, Ingrid.
Good night, Ingrid. Thanks for coming in. Feel free to stop in anytime, of course. So this ended up being about 800 images or so, because of just poor tracking, right? The target is going out of the field of view, that kind of stuff. I lost a lot more than what I sort of wanted to, but I've got about 800 images here that have been stacked, right, on top of one another. And the task here is to see how faint of a star can I actually see. So that was sort of the goal here. And yeah, this is really, really hard to look at like that. So I think what I'm going to do is I'm going to pull up my other chart here that I wanted to show you anyway. So let me see if I can try to walk you through this a little bit, help you identify some things. And this is the process that I'm going through. We're sort of going through this process together. I've looked at this a little bit already, but so let's go through it. Let's identify at least the bright things at first here. So I've got a bright star here and a bright star here, and see these dark tails that are coming off of it. That's I believe that is the result of the action of the physical shutter on the CCD camera. There's a shutter that opens and closes, and while while that's happening, the starlight is going to be diffracted around it, and it's going to hit the CCD camera, and we're going to see something. So I think that's what this is just a diffraction effect of the shutter. It's extremely low level. So at this point, I'm not worrying about it. Yeah, I don't know. You know, that is probably going to set a limit in terms of how accurate and precisely I can measure things. But I think at this point, it's sort of not too significant, right? Anyway, so this bright star, right, this bright dude right here is this bright star right there. Okay, so I tried to rotate this sort of as well as I could, but it isn't perfect. So you're going to have to do some mental gymnastics here, which isn't all that bad. So
I hope it doesn't put you on an eye strain and make you go blind.
yeah, no.
Because right now I think I might have got a little strain right now.
Dots. There's lots and lots of dots. Absolutely. Let's actually let's switch this around like that. That might make it actually easier to see what I'm going to be showing you. So here's the bright guy, right? And then you see this pattern here. It sort of goes this way, and then that, right? That's this right here. So this one is this one, and then there's the bright one, and then way down here is this one.
Now, are there any double stars in this image?
Well, technically speaking, the actual target object itself, which is this guy right here, this star is XY Canis Minoris. Technically speaking, that's a binary star. It's an eclipsing binary star. I don't know if any of these other ones are or not. Can't be sure about that. So do you see that pattern there? That's these three stars are these three stars. So if we sort of continue down, we see this one and a faint one right next to it. And that's this one and a faint one next to it. I'm going to zoom in a little bit here. Okay, so we started way up here, and we went from faint to really bright to faint to fainter to really faint, and that's this line here. Do you see that? And then, as you can see, it sort of takes a turn and goes to these two bright guys right here. And so this is where it takes a turn and it goes to these two bright guys. So this one, we'll scoot down a little bit. So this one and this one is this and this. And you can see that that one's there. Okay? And then if you take these two and sort of go off that away, right, you'll see these two. And that's these two guys right here. And these two guys point to these two. And this guy that's marked with a red dot, I don't know if you can see that or not on my screen. That is the target object. So that's XY Canis Minoris. But you can also see, you know, there's a triangle here. Here's a triangle. There's this star and this star, this star and this star. So now that I hope that you can sort of see that pattern, let's see how faint we can actually go. So the smallest dots on here are about 19th magnitude. The next larger ones are about 18th, and then the next larger ones are 17th, and it goes up from there. So the question is, how faint can we actually go here? And, well, you see how this makes a little triangle, and there's a little triangle here, so we can definitely see that. And that's probably about maybe 16th or so. If we move over, so go past these two over to this little triangle, let's see if we can see this little guy right there. So if you go past these two, little triangle, I'm seeing something there, right? That's a toughie. Let me center in on it here. Okay, so I'm saying that this and this and this are these three right here, or these three. And this guy is probably about maybe 17th or 18th magnitude.
And we're also going to have to say goodnight to Jim.
All right, Jim, take care. Thanks for coming in. Appreciate it. So I'm thinking that I'm seeing down to maybe about 18th, just barely. Sort of have to use a little bit of imagination, right, on that. But there's definitely something there, right? So this is about a 40-minute exposure. And I can see down to, for sure, 17th, maybe 17 and a half. But yeah, I'm a little...
You sure are hacking that telescope for sure.
Yes, I want to see what its limitations are, right? Because those are the kinds of things that I want to be able to advertise and say, hey, with this kind of exposure, you can expect to see this. So I want to be able to advertise those kinds of things, and I just want to know for my own work. So, but yeah, there are a few other oddballs in here that I'm not quite sure. I'm not quite sure what is going on with a few of these things. Let's see. Here's a really, really obvious one. Let's bring this over. Let's bring this over here. So, see this big one right here? That's this one. I almost have the size of the dots exactly right. That's pretty amazing. So, as you can see, there's something here in my data that would definitely show up if it was a star, I would think. So here's sort of a funny thing. Here's a pattern, right? 1, 2, 3, 4. I see 3. I don't see number 4. So this is kind of a funny thing. These two are funny things. So, yeah, not quite sure what any of those things are yet. Here's another one, right, where I can see that is probably this one and this one, right, or these two, but there's nothing that bright next to this one. So that's kind of a funny thing too. So, but I'm pretty happy with that. As I just said, if you sort of use your imagination, I think we're seeing 18th magnitude stars. For sure, 17th magnitude stars. So I think that's pretty nice.
I like it too.
Yeah. I have to investigate this slope. See, it's extremely obvious here, that it is definitely brighter sort of in this corner than it is over here. And that has to be some kind of systematic thing. That's not that's not anything in the sky, right? You know, the sky is pretty flat, especially on these scales. The size of this field of view is about 12 arc minutes on a side, more or less. So about a quarter of the size of the full moon. It's a very, very small patch of sky. So the sky background isn't going to vary as much as this. So this is some kind of systematic thing that I have to investigate a little bit, because I definitely don't want it there. So we'll see. We'll see how that goes. But yes, so this is the deepest image my system has taken so far. So 17th magnitude for sure, maybe 18th if you use your imagination a little bit. So I like it. Yay.
Now, what are your plans for your next observation session?
Yeah, I don't know yet, but that actually leads me into something that I was also starting to talk about yesterday, and you know, that's, I say this all the time, but you know, that's one of the great things about having a daily live stream is that I don't feel as though I need to rush or hurry. You know, if I don't get to something today, it's likely, in my experience, it's likely that tomorrow will come, and we'll be able, you know, to do it then. So that's exactly what is going to happen in this case. I sort of came across a what's turning out to be a fairly interesting eclipsing binary star in the constellation of Virgo. It's called HW Virginis, and it's right in the constellation of Virgo. It's again one of these eclipsing binary stars where you have at least two components, and you know, they're going around each other in some way, and you can designate each one. You know, the A component is usually brighter, and the B component is usually fainter. Now that doesn't say anything about how massive they are, their ages, nothing at all. Just, you know, one is brighter, one's fainter, and they're going around each other, right, in some kind of orbit. And it just so happens that orbit lines up with our line of sight. So what we see is a star, right, that is keeping the same brightness, keeping it. All of a sudden it dips, and then it rises again, and it maintains. And sometimes, and actually I'll show you some plots here, there are some other interesting structures in that light curve. But what's happening there is that the B component is passing in front of the A component. So for that period of time, you're basically only seeing light from the B component, right, and none from the A. Usually you're seeing light from both. But when B is like this, then you're only seeing B. And when B is behind, you're only seeing A. So there are oftentimes sort of a double dip in the light curve, and that is sort of characteristic of eclipsing binary stars. This particular eclipsing binary star has an orbital period of 2.8 hours. So, you know, um, you have to imagine uh, uh, what that might look like. You've got these two stars that might be actually in contact with one another. It's hard to know, but they're so close to one another that every 2.8 hours they are making one orbit. That just blows my mind. I have a hard time imagining things that large moving that fast. But that is really, really, really moving. And the interesting thing about this particular eclipsing binary star is that they think that they have discovered at least large planets in this system that are orbiting. You've got this very, very, very close binary system, and you have planets that are way out that are orbiting this pair of stars. So, again, imagine being on a planet, right, orbiting a binary star. Your orbital period might be days or years, and you can sit there and watch this binary star system rotating, right? It's got to be an amazing sight. It's got to be a totally amazing sight. So yeah, if the conditions are right, one can observe these eclipses maybe 3 times a night. So that object, right now Virgo is sort of rising. So it's a good time to catch this object, because it's coming up, as soon as the sun sets, or a couple hours after the sun sets, that object is up, and during the course of that night, it's going to do an eclipse every 3 hours or so. So you can usually see 2 or 3 of those in a night. So that is definitely one of my targets. That has gone way high up on the list. The other really cool thing about this one is that the difference between when it's brightest and when it's faintest is almost 1 magnitude, right? So almost a factor of 2.5. So easily detectable. I'll be able to see it in this scope, no problem at all, no problem. And I'm really, really anxious, to see that. And I might actually devote a whole night to a single orbital period. So I'll watch the dip, I'll watch the primary dip, then I'll watch the secondary dip, and then I'll watch the primary dip again, and then I'll be done. And that whole process will only take about 3 hours. So that sounds interesting. Anyway, let's get into XY. I'm sorry, HW Virginis a little bit more. I've as you can tell, I've already sort of dove into it a little bit. So let me share my screen here. Maybe. If I push the right buttons. Share the screen. There we go. Good job. Hide that away. And let's go to Simbad. So I've already pulled it up here. So this system is also extremely interesting because these two stars are both dwarf stars, very, very small, actually relatively low mass stars. One, the A component, the brighter of the two, is a looks like a B2 star. So it looks like a very, very, very massive hot star. But what it actually is the core of what was a red giant star. So it's just the core that's left, and it's sort of getting into its helium stage. So it is just beginning to sort of, as they say, burn helium. There's helium fusion going on. At least that's the story. So it's burning really, really hot, but it's pretty low mass. And the B component is an M dwarf star. So it's a very, very low mass, very, very cool star. And that's why it's darker, right? That makes sense. So this actually has a, well, you know, it has all the usual names, a bunch of different names. One of the ones that popped out to me is this PG. This is the Palomar Green Survey, which identified very, very what are called blue objects, very, very blue. Not, you know, the other way to say very, very blue is to say not very red. So and you know, blue objects tend to be hot. They tend to be massive, but in this case, it's just hot. It's just really, really hot. So very, very well studied. Lots of references, lots of references. We're going to look at a couple here shortly. There are some distance and velocity measurements. All look pretty consistent. Let's see, they're clocking it at 172.5 parsecs. So 1 parsec is 3.26 light years. So times 172.5. So that's 562 light years away. So, you know, that's getting kind of far. It's a little bit far, you know, for this bright of a star. Yeah, that's getting a little bit far out there for sure. Let's see, it's got a velocity of negative 9.1 kilometers per second. So I think that means it's coming towards us radially, right? So it, you know, all things are moving in 3 dimensions. So that's actually what this proper motion is here. We would actually be able to measure the actual velocity in kilometers per second. But we astronomers, we like to confuse things. So the motion in the plane of the sky, right, in right ascension and declination, are usually expressed in milliarc seconds per year. So not kilometers per second, but milliarc seconds per year. So that's what these numbers are. So this indicates that it is moving in a positive right ascension. I'm going to zoom in a little bit here. Maybe you can't see that very well. Positive right ascension, which means it's moving east, and a negative declination, which means it's moving south. So it's moving south and east in the sky, and then it's coming towards us. So what that means is that, yeah, you know, it might be coming towards us in a radial way, but it's moving to the south and east of us, so it's going to miss for sure. Parallax, that's just an indication of distance, and wow, there's a lot of discrepancy there. So yeah, don't really know what's going on there. I suspect that this is probably Gaia, this 2018 reference here. So yeah, don't know. Spectral type. Okay, cool. I think I've got a paper already pulled up here. So why don't we just take a look at this one? So this is from 2004, right? So I mean, that's a pretty long time ago. This particular object, I think, was discovered to be an eclipsing binary star back in 1986. I think is the. In fact, you know, we should look and see if we can find that reference. That'd be an interesting reference to look at. So let's go back. These are very, very nicely in date order. So we can just swing on back to good old 1986. So here is the PG catalog that I was referring to. It might be this one. Yeah, it's got to be either this one or this one. It's got to be this one. Let's find out. Let us find out. Take another big gulp of this HOH. So they're calling this pre-cataclysmic binaries. Compilation of the orbital parameters of 22 pre-cataclysmic binaries together with a discussion of the observational data is given.
I was T-minus 14 months when they released that paper.
Oh, yeah? Boy, that makes me feel old. I was, let's see, in 86, I was 16, 17. I think I was 17 most of that year. So let's see, here we go. Let's see if it's on our list here. I'm not seeing it. Physical parameters. It might be under a different name. Yeah, I think this one's it right here. 3477. Let's go back to Simbad. I think it had its BD. Yeah, BD. Oh, BD 073477. I think that's what that said. Yes. There it is. Okay, so here it is. And wow, well, there's not a lot of info on that.
Wow.
Yeah. They just sort of identified it here. That's about it. So let's see what else they say about that. Let's do a search. I think I don't know if I can do a text search or not here. Let's find out. 3477.
Give it some time.
Yeah. Give it some time. Give it some time. I don't think it's going to. I don't think that this is texted. All right, so we're going to have to do it the hard way. We're going to have to look through this. Now they're calling this name. So that's what we have to look for. Is 3477. So that's not going to be easy, but I will certainly try. And to anybody who's watching, give a shout if you see it, because they should talk about it a little bit. They're talking about everything else here. Oh, there it is. So it's found to be an eclipsing binary, roughly of magnitude 10.5 outside of the eclipses, and a partial primary eclipse of about 0.7 magnitude, and a secondary eclipse of 0.1, and a reflection effect. Wow, okay, I don't know about these reflection effects. Huh. So, yeah, this is the discovery paper of this guy, 1986. So there it is. Yay! Look, we're only halfway through this paper, so let's quickly let's see, what are they talking about here? Okay, yeah. So yeah, they're getting into the models and trying to understand what these things are doing. So there's all kinds of math and stuff. This is just algebra, though. I mean, there's nothing complicated here. You plug in numbers and you get a result. This is just computation. Blah blah blah.
Please excuse my dear Aunt Sally.
So I'm looking for 3477 still. Okay. It just, I know I say this all the time, but it just, it completely amazes me how much work goes into these kinds of things. And it's great. Okay, well, I didn't see it anywhere else. They, after they talked about their data, they went into the model. So yeah, that's sort of what the rest of that is about. So, well, let me show you some light curves, and then we'll get on out of here. So let me show you this paper. So this is as of 2004. There are more recent ones as well, but this one, I don't know if this was the discovery paper of this new third object or not, but I guess they talk about it here. And wow, so these guys are in Turkey. Wow, that's awesome.
That's usually a good summer listen, the voice of Turkey.
Oh, is it?
Yeah.
Cool. Yeah, so here is the reference to the discovery paper. Oh, and I guess there's a light curve from back then too. Oh, I didn't see that. These are two different papers, it looks like. So yeah, we'd have to investigate that a little bit.
And
Um,
speaking of the voices circulating around shortwave, the A19 is underway.
the what is underway?
The 2019 summer schedules are underway.
Hmm. Cool. All right. Let's. Okay. So here's some light curves. Let me try to zoom in here a little bit more. Maybe even a little bit more. You can really see what's going on here. So they plot this oftentimes in sort of weird ways that to me are kind of hard to understand when you're first looking at this. But I'm going to try to go through it anyway. So they're looking at this object at two different wavelengths. Or filters, right? They're using a V filter and a B filter. And in this case, V looks like it's brighter than B. Whatever. So then, along this axis, they're showing phase, which you can imagine as an orbital phase. At some point, which they have to, sort of arbitrarily designate, is phase 0, and then the phase goes from 0 to 1, and when it reaches 1, that's one orbit, right? So half a phase is, I'm going to zoom in even a little bit more. So I hope that makes sense. I wonder, can I, trying to think if there's a way that I can show that a little bit better. Well, for now, I'm just going to continue. So they designate a phase of 0 at this lowest point, and that's when the secondary star is directly between us and the primary bright star. And so it's all that we're seeing right at this bottom point is just light from that darker second star, and that's why it looks fainter. So that is phase 0. So of course, phase 0.5 is when that secondary darker star is directly behind the primary star. And at that point, you're only seeing light from the bright primary star. Everywhere else here, you're seeing some form of light from them both. And I guess what they're talking about in terms of the reflection effect is this. You see how, it's not flat. It's going up, and then it's down, and then, so this has these big long wings. I guess that is the reflection effect that they're talking about. So that's kind of interesting. So yeah, there's sort of a typical light curve for these kinds of eclipsing binary stars, and the time between here and here is the 2.8 hours. It sort of repeats itself, right, over and over and over and over and over again. So yeah, that's a nice nice light curve. Very little scatter in the data. That's nice. And when these things dip, you definitely see it. So yeah, I'm kind of anxious to see this from myself, for sure. So yeah, so what they can do is they can measure when these dips occur, right? Pretty precisely. And then they can compare that timing to what the models say. They can build a model of this system that has, you know, 2 stars with these kinds of parameters. And from that model, you can generate a light curve. And from that light curve, you can predict when these low points are, say. And if there are differences between what you observe and what you predict, well, then you have to account for that in some way. And that's actually what this is showing, is that they are looking at, you know, the differences between the model and the observation, and they're seeing this periodic difference, right? The difference is changing over time. And one of the ways to account for that is to introduce a third body, which is making this wobbling motion. And so that's sort of what they've done here. And so, yeah, it does. I mean, that looks like a pretty good fit. These dots down here, these points down here, I can zoom in again. Yeah, that's much better. So these points here is just what's called the residual. So it's the data point, these dots minus this curve. So you can see that it, you know, we're talking about very, very, very small changes. You know, what the amplitude of this thing is like 0.002 days, which is what, 0.002 times 24. That's 0.048 hours, which is 173 seconds. So they were seeing a discrepancy in the timings of no more than 173 seconds. And that slight little amount can more or less be accounted for if you assume that there's a third body in there. So, but even if you look at the residuals here, there's some structure in there still. So there may even be smaller bodies in there as well, or the parameters of this third body aren't as well known. But, you know, that's a pretty good fit. Yeah, it's a pretty good fit. So it's kind of neat. This is a way of you know, potentially detecting you know, third or fourth or fifth. You know, this may be a means. You know, with instruments like TESS that are up in orbit and not subject to any of the atmospheric distortions or anything. TESS has the capabilities of actually seeing micro magnitude differences between things. And so, you know, TESS is primarily interested in looking for planets that are transiting stars, but there's absolutely no reason why it can't be used to observe eclipsing binary stars and get some very, very, very accurate timings to see if you can not only, and I think that this is very, very cool, you can not only use TESS, you know, for how it was built, but you might be able to detect planets in this other way. So, you know, TESS might be actually able to detect planets 2 different ways. So very, very cool. All right, everybody, I'm going to get out of here for now. There's a little bit more to talk about when it comes to HW Virginis. So I think we're going to stick on that for a little while. I don't think it's supposed to be clear tomorrow. I think it's supposed to be cloudy again. So, so that means for sure I will be here. So 2 hours UTC, just about 22 hours and 35 minutes from now. I will be back here, and I hope that you can join me. And, you know, don't feel as though you have to come in each and every day. I'm glad you do if you do, but definitely don't have to. This is a casual crowd, so you come on in whenever you can or want to. We are easy here. So, all right, everybody, take care. Peace, cheers, and all that. Live long and prosper.
Live long and
And
prosper.
yes, sirree. All right, take care. I will see you in just a short spin. That's it. All right, everybody. Bye.
Later.